Hello, Assalamualaikum. Very good day, everyone. Today, we will continue our lecture on fundamental concept in chemical process engineering. So today, I will focus on how to calculate degree of freedom analysis for single unit system. Okay. Let's have a look at the examples. I hope that you are clear on this degree of freedom analysis, DFA. Okay, so for today, we are going to go to solving the matter balance on a single unit, and we are going to touch on concept of DFA to solve our problem, and why it would be important when we start to get the complex processes. So let's take a look at this distillation column, in which we have three components: A, B, and C, all entering the columns, and we have A, B, and C as outlets at the outlet stream. Okay, we can see that this column performs some kind of process to separate these three components. As you can see, uh, first stream, A component, and then middle stream, we have A, B, and C components, and bottom stream, we have B and C components. Okay, so as an engineer, your job is to perform meter balance so we can solve for the unknown flow rate of our stream, as well as the composition that we may not know. In this case, we have two unknown mass fraction. Okay, and here we have additional info provided in this question. Mass flow rate at stream 3 is half the flow rate of stream 1. Okay, what's this? Okay, later I show you. Yeah, for this the second additional info. For instance, here we have unknown flow rate M1, M2, and M5. Okay, we express M1, M2, and M5 according to the number of streams. So you can denote stream 1, stream 2, stream 3, 4, and 5. And then we also have unknown composition, X2 for stream 2 and X4 for stream 4. So we have designated it X2, and the remaining must be 1 minus X2 for component A, mass fraction for component B, X2. Okay. And then we also don't know the composition in stream 4 for C. Okay. So we can design it X4 for C, and then the mass fraction for component A is 0.7. So 1 minus 0.7 is 0.3. So we can get mass fraction for component B by 0.3 minus X4. So you can get, we call it mass fraction for component B and component C. So based on this, what you call it, the BFD, we can break down to the ideas that we take all of our unknown and we quantify how many we have, an equation that we can use to help to solve for the unknown by taking to the unknown minus the known equation for DFA. DFA must be 0 in order for us to calculate or to identify unknown values. Okay. So next we have to identify. We already identify unknowns. We have 5 unknowns. Betul? Dapat tak? We have 5 unknowns. M1, M2, M5, X2, and X4. Even though we can write overall balance for this, we call for this material balance for this problem, but because the overall balance consists of A, B, and C, so that equation is dependence. Okay, so at the end we have 5 unknown. So we need, when we want to determine the DFA, we take number of unknown minus number of balance. We have degree of freedom of 2. So, unknown minus balance minus number of relationship. So we have number of unknown 5 minus 3 materials A, B, and C. And then we have another additional info, which is M3 is half the flow rate of M1 and 90% of C in M1 exit in M5. So we can get a magic number for the FA, which is 0. 5 minus 3, 3 materials. Remember, in this case, we have A, B, and C components. So we have 3 number of balance. Okay. So 5 minus 3 minus 2, 2 comes from these 2 additional info. So DFA equals 0. Because we get the magic number, we know this problem is solvable. Okay, next. So first thing we do is write our balance. We can start with our balance, or we can start with A, B, or C balance. Usually, I like to start with overall balance. Okay, so our balance is M1 plus M2. M2 already given 5,300 kg per hour. M in equals M out. So M1 plus 5,300 is M in minus M3 unknown, M4 1,200 and M5 here. So this is our balance. Okay, and then we can write balance for component B. So we can get this equation, and then write equation for component C. Okay, M in equals M out. Next. And remember, you can write down the additional info into this equation. M3 equals 0.5 M1. And then 90%, we can put 0.9 times C of C in M1 as it. So 0.97 M1 equals 0.4 M5. Okay. So at the end, you have these 5 equation. Kalau tak dapat, bagi tahu saya, nanti kita buat nanti kalau if you have any problem to come up with these 5 equation, let me know. I can explain to you, okay? So by solving equation, all these 5 equation, you can get unknowns value M3 equals this one, M5, and then by substituting the M1 into any equation, you can get M3 into equation 3, you can get M5, okay? So by substituting M1 into this, I think, yes, M1 and then M2 into this equation, you can get X2 and so on and so forth. So this is the final answer. So at the end, you can put all the unknown values in your materials balance. So this is the final answer. Okay. And this slide, I want you to calculate this problem. A continuous distillation column is to be used to separate a three-component mixture of acetic acid, water, and benzene. Three components, yeah. And a trial run gave the data below mass basis. The data for the benzene in the feed, which consists of AA, W, and B, was not taken because of an instrument malfunction. So use a degree of freedom analysis and then calculate the benzene flow in the feed in kg per hour. So this is the answer for benzene flow in the feed here inlet total in kg per hour. So hopefully you can get this answer by using DFA analysis. Okay, that's it for first. That's it for me. Okay, thank you. Assalamualaikum.